Hello everyone, I am Bireshwar Roy. I am currently pursuing my 4th year PhD in the Department of Physics, Indian Institute of Science, Bangalore. I am currently working in the field of experimental condensed matter physics. In this video, I will be discussing all the questions from the topic electromagnetism came in the exam GATE Physics 2021. This question was asked from the GATE Physics paper 2021. This is a MCQ type 1 mark question and this question is from the topic Electromagnetic Theory. The question is, a matter wave is represented by the wave function psi as a function of xyz t equals to a e to the power I 4x plus 3y plus 5z minus 10 pi t, where a is a constant. The unit vector representing the direction of propagation of this matter wave is, these are the 4 options we are given. So we have to choose the correct one, which basically representing the unit vector along the direction of propagation. So let us see the solution. So our matter wave is given by this equation. It is clear that this is a plane wave equation. Plane wave equation has the form psi as a function of xyz t equals to a e to the power I k dot r minus omega t, where k is the propagation vector or the wave vector of this wave, r vector is the position vector and omega is the angular frequency of this wave. In our case, k dot r equals to 4x plus 3y plus 5z, which is written here. Now, if we just expand this dot product, then we will get kxx plus kyy plus kzz equals to 4x plus 3y plus 5z. Now, we will compare individual component of this k from left side to right side. So, basically it will give kx equals to 4, ky equals to 3 and kz equals to 5. So our wave vector is 4x cap plus 3y cap plus 5z cap. Now in order to find a unit vector along this propagation vector, what we will do, we will take the magnitude of this k vector, then we will calculate the k vector divided by its magnitude, which will basically give 4x cap plus 3y cap plus 5z cap divided by root over 4 square plus 3 square plus 5 square. After simplification, we will get 4 by 5 root 2 x cap plus 3 by 5 root 2 y cap plus 1 by root 2 z cap. So among the 4 options, the first option, option A, is the correct answer, which is basically representing the unit vector along the direction of propagation of this matter wave. This question was asked in the GATE Physics paper 2021. This is a MCQ type 1 mark question. This question is from the topic Electromagnetic Theory. The question is, consider a tiny current loop driven by a sinusoidal alternating current. If the surface integral of its time averaged Poynting vector is constant, then the magnitude of the time averaged magnetic field intensity at any arbitrary position r vector is proportional to option A 1 by r cube, option B 1 by r square, option C 1 by r, option D r. So we have to choose the correct option. Let us see the solution now. We have to consider a tiny current loop. Now a tiny current loop is basically analogous to a oscillating dipole. So we can consider a tiny current loop as a oscillating dipole whose Poynting vector is S vector equals to E cross H, where E vector is the electric field and H vector is the magnetic field intensity. It is also given the surface integral of its time averaged Poynting vector is constant. So the time average of S vector will be this, and which is basically time average of E cross H. Now, according to the question, the surface integral of the time averaged Poynting vector is constant. In the surface integral, this dA vector is the differential surface area vector. Now, if we represent this dA vector in the spherical polar coordinate, then it will become r square dr sine theta d theta and d phi. So, basically dA vector is proportional to r square. So, if the surface integral is constant, then it will lead to this time averaged Poynting vector will be proportional to 1 by r square, so that this surface integral will be constant. Now, from this we can conclude our time averaged electric field vector will be proportional to 1 by r, and the time averaged magnetic field intensity will vary as 1 by r. If you remember the case of oscillating dipole, for an oscillating dipole, both the electric field and magnetic field varies as 1 by r. So, among these four options, the option C is the correct answer, that is 1 by r. This question is from the GATE Physics paper 2021. This is a MCQ type question having 1 mark, and the question was asked from the topic Electromagnetic Theory. The question is, consider a solenoid of length L and radius capital R, where capital R is very less than L. A steady current flows through the solenoid. The magnetic field is uniform inside the solenoid and zero outside. So this is the schematic we are given. Among the given options, choose the one that best represents the variation in the magnitude of the vector potential 0, Fi 0. These are the three components of the vector potential at z equals to L by 2 as a function of radial distance small r in the cylindrical coordinates. We are also given a useful information, that is curl of a vector in the cylindrical coordinates. So these are the four options which shows the variation of the vector potential at z equals to L by 2 as a function of radial distance small r. So we have to choose the correct option which represents the variation of vector potential as a function of small r correctly. So let us go to the solution part. So we'll consider a solenoid having radius capital R and length L, and the current is flowing through the solenoid along phi cap direction. The axis of the solenoid is along z cap direction, and as the current is flowing along the phi cap direction, so our magnetic field in the solenoid will also be along the z direction. It is also given the radius of the solenoid is very less than of its length. So basically it will be considered as a long solenoid. Now we know for a long solenoid the magnetic field inside the solenoid will be constant, and that is given by mu naught Ni z cap, where mu naught is the magnetic permeability in the vacuum and N is the number of turns per unit length and I is the current flowing through the solenoid. And in the outside region of the solenoid, the magnetic field will be 0. Now current is along phi cap direction. So eventually the vector potential will also be along phi cap direction. We have to find the vector potential. So basically expression for vector potential both inside the solenoid and outside the solenoid. Now we'll consider the first case, that is smaller less than radius of the solenoid. So this is basically the region inside the solenoid. For this we'll consider a circular path of radius smaller at position z equals to L by 2. We will calculate the closed path integral of vector potential along this circular boundary. Now this line integral can be written as surface integral of curl of the vector potential. And we know the curl of vector potential is basically our magnetic field. So it can be written as the surface integral of B vector. Now inside the solenoid the magnetic field is constant, and that is mu naught Ni. So we can easily calculate this surface integral as mu naught Ni multiplied by pi small r square, where pi r square is the area of the circular region. And also from the symmetry consideration, the vector potential will be same along the boundary. So we can calculate this line integral as mod of a vector multiplied by 2 pi r, where 2 pi r is the length of the circular boundary. So our vector potential at position small r will be mu naught Ni by 2 multiplied by small r, and in the vector form it will be mu naught Ni by 2 multiplied by r along the phi cap direction. Now we will consider the second case, that is smaller greater than radius of the solenoid. For this, we will consider a circular path having radius smaller at position z equals to L by 2. So now our small r is greater than capital R. We will do the same treatment, and for that we will take the closed path integral of the vector potential along the circular boundary. And we can write this line integral as a surface integral of the magnetic field. Now magnetic field inside the solenoid is constant, that is mu naught Ni, but outside the solenoid the magnetic field is 0. So we will split this surface integral into two parts. So one is for inside the solenoid and other one is for outside the solenoid. For inside, the V vector is constant, that is mu naught Ni, and the surface area will be pi capital R square. So this first part will be mu naught Ni pi capital R square. But the second part, the B vector is 0, because outside the solenoid the magnetic field is 0. So eventually this second integral will give us 0. And for the line integral, closed path integral of the A vector, this will be mod of A multiplied by 2 pi r. So our vector potential will be mu naught Ni capital R square by 2r, and in the vector form this will be mu naught Ni capital R square by 2 small r along the phi cap direction. As of now, we have calculated the vector potential for both inside the solenoid and outside the solenoid. So if we see the expressions of vector potential, then the A phi is proportional to smaller for inside the solenoid, and it is proportional to 1 by smaller in outside of the solenoid. So if we plot this plot will look like this. So among the four options, this option C is representing the variation of the vector potential as a function of radial distance smaller correctly. This question is from the GATE Physics paper 2021. This is a MSQ having 1 mark, and the topic of the question is electromagnetic theory. The question is, as shown in the figure, an electromagnetic wave with intensity I with subscript I is incident at the interface of two media having refractive indices n1 equals to 1 and n2 equals to √3. The wave is reflected with intensity I with subscript R and transmitted with intensity I with subscript capital T. Permeability of each medium is the same. The reflection coefficient is defined as capital R equals to I with subscript R divided by I with subscript I, and the transmission coefficient capital T is defined as I with subscript T divided by I with subscript I. So we have to choose the correct statement. Option A is R equals to 0 if theta I equals to 0 degree and polarization of incident light is parallel to the plane of the incidence. Option B T equals to 1 if theta I equals to 60 degree and polarization of the incident light is parallel to the plane of incidence. Option C, R equals to 0 if theta I equals to 60 degree and polarization of the incident light is perpendicular to the plane of incidence. And option D, T equals to 1 if theta I equals to 60 degree and polarization of the incident light is perpendicular to the plane of incidence. So as this is a MSQ, so it is possible to have multiple options correct for this question. Let us see the solution part now. According to our question, we have an interface separating two media having refractive indices n1 equals to 1 and n2 equals to √3. Now, one unpolarized light is incident on the interface with angle of incidence theta I and the angle of reflection is theta r and the angle of transmittance is theta t. Now, the reflection coefficient r is defined as IR by II and the transmission coefficient is defined as T equals to IT by II, where IR is the intensity of the reflected light and II is the intensity of the incident light and IT is the intensity of the transmitted light. Now we will first calculate the Brewster angle theta b at the interface. First let us discuss what is the Brewster angle theta b. So Brewster angle theta b is basically the angle of incidence of an unpolarized light on an interface such that the reflected light will have only the component of S polarized light. That is, the reflected light will have electric field only the perpendicular direction of the plane of incidence. There will be no component with the electric field in the parallel to the plane of the incidence. That is, p polarized light will not be there. So according to the Fresnel's equation, the reflection coefficient for the p polarized, that is the parallel component, is tan of theta I minus theta t divided by tan of theta I plus theta t. And the reflection coefficient for the S polarized light, that is the perpendicular electric field to the plane of incidence, is minus sine theta I minus theta t divided by sine of theta I plus theta t. Now if we look into these relations carefully, we can see for the first relation, if the theta I plus theta t is 90 degree, then this tan of theta I plus theta t is infinity. So effectively we will get this r parallel is 0. But for this condition theta I plus theta t equals to 90 degree, this r perpendicular is not equal to 0. So from this condition we can get the estimation of Brewster angle. So under the condition of theta I plus theta t equals to 90 degree, only the S polarized light, that is the light with electric field in the perpendicular direction of the plane of incidence, will get reflected and theta I will be known as Brewster angle. Now we will use the Snell's law to estimate the Brewster angle. Now under this condition, the angle of incidence theta I is basically our Brewster angle, that is theta b. So by applying this Snell's law, we will get sine theta b by sine theta t equals to n2 by n1. Now our theta t is basically 90 degree minus theta b according to our condition for Brewster angle. So effectively we will get sine theta b by cos theta b. So our n2 by n1, basically sin theta by cos theta b, that is tan theta b equals to n2 by n1. Now according to our question, n2 value is √3 and n1 equals to 1. So in our case the Brewster angle is tan inverse n2 by n1, that is tan inverse √3 by 1. So theta b equals to 60 degree. Now we'll consider 2 points. First point is, if the polarization of the light, that is E vector, is in the plane of incidence, that is P polarized light, then at the angle of incidence theta I equals to theta b, we have the reflection coefficient equals to 0 and the transmission coefficient T equals to 1. So this is the case of total transmission of p polarized light at incidence angle theta b. And the second point is, if the polarization of light, that is E vector, is in perpendicular to the plane of incidence, so this is S polarized light, then at the angle of incidence theta equals to theta b, we have the reflection coefficient not equal to 0 as well as the transmission coefficient not equals to 1. So this is the case of partially reflected and transmitted light for the S polarization case. Also, for the angle of incidence theta equals to 0, that is normal incidence, the reflection coefficient not equal to 0. So if we consider all the points, then we can conclude only our option B is correct for this question. According to our solution, the correct option for this MSQ is only option B, that is T equals to 1, that is transmission coefficient equals to 1 if angle of incidence theta I equals to 60 degree and polarization of the incident light is parallel to the plane of incidence. This question was asked from the GATE Physics paper 2021. This is a multiple select question of 1 marks, and this question was asked from the topic electromagnetic theory. The question is, a material is placed in a magnetic field intensity capital H. As a result, bound current density Jb is induced and magnetization of the material is capital M. The magnetic flux density is capital B. Choose the correct options valid at the surface of the material. Option A is divergence of M equals to 0. Option B, divergence of B equals to 0. Option C, divergence of H equals to 0. And the last option, option D, divergence of JB equals to 0. Now, as this is a MSQ, so it is possible to have multiple options correct. We'll check each and every options one by one. Let us see the solution part now. Before going to the solution part, we will first recap some basics related to the magnetic material in a magnetic field. We know magnetization of a magnetic material when it is kept under an external magnetic field B, it provides us with a macroscopic description of the atomic currents in the matter. Mathematically, magnetization of a material is defined as summation over all the magnetic dipole moment of the matter divided by a volume element when volume tends to 0. Here, magnetization of the system is a macroscopic quantity, but your magnetic dipole moment is a microscopic quantity. If we want to visualize what is the magnetization of a system physically, we need to consider tiny current loops formed in the matter due to the cyclotron motion of the electrons when the material is kept under a magnetic field. Now, this tiny current loop will have some magnetic dipole moment. These magnetic dipole moments will basically contribute to the magnetization of the system. Now, for uniform magnetization, the volume bound current density Jb is 0, but the surface bound current density Kb is non-zero. This is because for uniform magnetization, all the tiny current loops formed inside the bulk of the system will cancel each other. Hence, you will have a 0 volume bound current density Jb. But at the surface, the cancellation will not happen. So, effectively, you will have a non-zero surface bound current density Kb. In the case of non-uniform magnetization, both the current densities Jb and Kb are non-zero. Now, we'll try to relate these current densities Jb and Kb to the magnetization of the magnetized material. For this, we'll consider a magnetized material kept under an external magnetic field B, and the system will have volume V. Inside this system, we'll consider an elementary volume dV, whose coordinates is x dash, y dash, z dash from the origin. And we'll consider another external point P, which has the coordinate x, y, z. So from the volume element, the external point P will have position vector capital R, which is basically your R vector minus R dash vector. Now we know vector potential due to single current loop having magnetic dipole moment small m is given by mu naught by 4 pi m cross r by r cube. Now for a magnetized material having magnetization capital M, the vector potential A vector is given by mu naught by 4 pi integration over M vector dV cross product with capital R vector by capital R cube. Now after some simplification with the help of vector algebra, we can show this A vector is basically summation of two terms. Now here the first term is due to the contribution from the volume of the system, that is the bulk of the system, but the second term is due to the contribution from the surface of the system. And from the first part, this curl cross M is basically your volume bound current density, and in the second term the M cross N cap, this is your surface bound current density. Hence the volume bound current density is defined as JB equals to curl cross M vector, and surface bound current density is KB equals to M cross N cap. Now we'll see the solution of the given question. We have already seen when magnetic material is placed in a magnetic field, it will get magnetized, and it will give rise to two types of current densities, that is volume bound current densities and surface bound current densities. The volume bound current density is given by JB vector equals to curl cross M, and your surface bound current density is KB equals to M cross N cap. Now we know the magnetic flux density or magnetic field inside the material is given by mu naught times your H vector plus the magnetization vector M. Now from the Maxwell's equations, we know divergence of B vector is 0. For a magnetized material, this B vector is mu naught times H vector plus M vector. If we put that relation in the equation, then you will get mu naught times divergence of H plus divergence of M equals to 0. It will basically give divergence of H equals to minus of divergence of M. Now our system has a volume bound current density JB. This means our system has non-uniform magnetization. So the divergence of M vector for this system is non-zero, and it will give rise to divergence of H is non-zero. Now divergence of JB is divergence of curl cross M, because JB is defined as curl cross M. And this term is also 0, so your divergence of JB is 0. So if you see the four options, among the four options, this B option and the D option is correct. According to our solution, the option B and option D, those are divergence of B equals to 0 and divergence of JB equals to 0 are the correct options for this question. This question was asked in the GATE Physics paper 2021. This is a MCQ having 2 marks, and the question was asked from the topic Electromagnetic Theory. The question is, an electromagnetic wave having electric field E vector equals to 8 cos kz minus omega t along y cap direction, and the unit is volt per centimeter, is incident at 90 degree, that is normal incidence, on a square slab from vacuum with refractive index N naught equals to 1 as shown in the figure. So according to this schematic diagram, an electromagnetic wave is incident on the surface 1 of the square slab at 90 degree. The slab is composed of two defined materials with refractive indexes N1 and N2. So in the square slab, two regions, that is green and blue, are divided by this diagonal, and this green region has refractive index N2 equals to 1.1 and this blue region has refractive index 2.2. Assume that the permeability of each medium is the same. After passing through the slab for the first time, the electric field amplitude in volt per centimeter of the electromagnetic wave which emerges from the slab in region 2 is closest to. There are 4 options given. Option A 11 by 1.6, option B 11 by 3.2, option C 11 by 13.8 and the last option, option D 11 by 25.6. So in this question, to solve this, we have to do basically we have to find the amplitude of the electric field in region 2 after getting reflected from this diagonal interface. Let us see the solution part now. According to the schematic given in our question, the electric field of the EM wave in region 1 is given by E vector equals to 8 cos kz minus omega t along y cap direction. And the EM wave is propagating along z cap direction in the region 1. Now, some portion of the incident EM wave in region 1 will be transmitted inside the slab and will fall on the diagonal interface separated by these two regions. Two situations may occur in this case. First one is the angle of incidence on this diagonal interface is less than the critical angle for total internal reflection. Then some portion of the incident EM wave will be reflected back in this region and the remaining portion will be transmitted from this interface in this region. The second possibility is the angle of incidence is greater than the theta c, that is critical angle for total internal reflection. Then total incident wave on this interface will be reflected back in this region towards this region 2. Hence, we'll first check what is the critical angle at the diagonal interface. Now, in case of total internal reflection from an interface, if the EM wave is incident on the interface at an angle equals to the critical angle theta c, then after reflection, the EM wave will travel along this interface. So the reflection angle is 90 degree. To find this critical angle in our case, we'll use Snell's law. Now applying the Snell's law, we'll get sin theta c divided by sin 90 degree equals to N2 by N1, which is basically 1.1 by 2.2. So our theta c, the critical angle for total internal reflection, is sin inverse half, that is 30 degree. And we have seen earlier that angle of incidence at this interface is 45 degree. So in our case, the angle of incidence at diagonal interface is larger than the theta c, which is 30 degree. So for sure, the total internal reflection will take place at the interface. As total internal reflection is taking place at the diagonal interface, then the intensity of the incident EM wave on this interface I1 will be equal to the intensity of the EM wave after getting reflected from the interface, that is I2. So I1 equals to I2 and I0 is the intensity of the EM wave in region 1, which is given by half multiplied with C epsilon naught E naught square, where E naught is given in the question, that is 8 volt per centimeter. Here C is the velocity of light or EM wave in vacuum, epsilon naught is the permittivity in vacuum. Now at interface 1, we'll apply the Fresnel equation for transmittance. As the EM wave is propagating along z cap direction and electric field vector is along y cap direction, so it is the EM wave with in plane polarization. Now for in plane polarization, the transmitter's formula is this, which is T1 equals to 4 N1 N0 by N1 plus N0 whole square. Now if we put the value for N0 N1 in this formula, we will get T1 is 55 by 64. So we get the transmittance for the interface of region 1 and this region. So the transmitted light from the region 1 to this region of the slab is given by I1 equals to T1 multiplied with I0, that is 55 by 64 into I0, which is your I2, because our I1 equals to I2 in this region because of total internal reflection. Now we will calculate the transmitter's value for this interface, that is interface 2, and it is given by T2 equals to 4 N1 N0 by N1 plus N0 whole square, which is same as the T1, that is 55 by 64. Now the intensity of the EM wave in region 2, that is given by I3, is basically T2 times your I2. Now T2 is 55 by 64 and I2 we have calculated in the previous slide, that is 55 by 64 I0. So your I3 is 55 by 64 whole square multiplied with I0. Now I3 can be written as half C epsilon naught E03 whole square, where E03 is the amplitude of the electric vector in region 2 and I0 is half C epsilon naught E0 square. So if we just cancel out the half C epsilon naught from both sides, then we have E03 whole square equals to 55 by 64 whole square times E0 square. So E03 is 55 by 64 E0. Now E0 is 8 volt per centimeter as given in the question. Effectively we have E03 in region 2 is 55 by 8. So if we just divide the numerator and denominator by 5, then we will get 11 by 1.6, which is our E03 in region 2. So our option A is correct. According to our solution, after passing through the slab for the first time, the electric field amplitude in volt per centimeter of the electromagnetic wave which emerges from the slab in region 2 is closest to 11 by 1.6, that is option A is the correct answer for our question. This question is from the GATE Physics paper 2021. This is a numerical answer type 2 marks question and the topic of the question is electromagnetic theory. So the question is, consider two concentric conducting spherical shells as shown in the figure. The inner shell has a radius small a and carries a charge plus q. The outer shell has a radius small b and carries a charge minus q. The empty space between them is half filled by a hemispherical shell of a dielectric having permittivity epsilon 1. The remaining space between the shells is filled with air having the permittivity epsilon naught. The electric field at a radial distance small r from the center and between the shells, that is r greater than a but less than b, is, four options are given. Option A is q by 2 pi times epsilon naught plus epsilon 1 times r squared along the r cap direction everywhere. Option B, q by 4 pi epsilon naught multiplied with 1 by r square along the r cap direction on the air side, and q by 4 pi epsilon 1 multiplied with 1 by r square along the r cap direction on the dielectric side. Option C, q by 2 pi epsilon naught multiplied with 1 by r square along the r cap direction on the air side, and q by 2 pi epsilon naught epsilon 1 multiplied with 1 by r square along the r cap direction on the dielectric side. Option D is q by 4 pi times epsilon naught plus epsilon 1 multiplied with 1 by r square along the r cap direction everywhere. So let us see the solution part. According to the question, we are given two concentric spherical shell. The inner shell has the radius small a and the outer shell has the radius small b. As the spherical shells are conducting, the plus q charge will be uniformly distributed over the surface of the inner shell, and the minus q charge will be uniformly distributed over the outer shell. The empty space between the two shells is half filled by the hemispherical shell of a dielectric having permittivity epsilon 1, and the remaining part is here having permittivity epsilon naught. Now the dielectric in the region between these two spherical shell, that is hemispherical part, will be polarized, and because of the polarization there will be formation of bound charges in this dielectric medium. Now the displacement vector in the air is given by d naught vector equals to epsilon naught times electric field vector E, and in dielectric it will be d1 vector equals to epsilon 1 times E vector. We only have the information about the free charges, not the bound charges according to the question. So we will use the Gauss law in terms of the d vector, that is surface integral of the d vector is free charge enclosed by this surface. So according to our schematic, the closed surface is the dotted line. So the free charge enclosed by the surface is only plus q. So we can write this surface integral as d naught times 4 pi r square by 2, which is the surface area of the closed surface in the air region, that is 4 pi r square by 2, plus d1 times 4 pi r square by 2, which is also the surface area, that is the half of the spherical surface area in the dielectric region, and the free charge enclosed by the surface is plus q. So we can take this 4 pi r square by 2, that is 2 pi r square, as common, and we will have 2 pi r square times d naught plus d1 equals to q. We can write it as 2 pi r square times epsilon naught e plus epsilon 1 e. So which is basically our displacement vector d naught and d1 equals to the free charge enclosed by the closed surface, that is plus q. So we'll take E, the electric field, as common. So we'll get 2 pi r square E times epsilon naught plus epsilon 1 equals to q. So our electric field is q by 2 pi epsilon naught plus epsilon 1 times 1 by r square. The direction of the electric field in the region r greater than a but less than b region will be along radial direction, that is r cap direction, as the charge distribution on the spherical shell surface is spherically symmetric. So the electric field vector in the region will be q by 2 pi times epsilon naught plus epsilon 1 times 1 by r square along the r cap direction. So our option A is correct. So according to our solution, the electric field at a radial distance small r from the center and between the shells, that means in this region, is option A, q by 2 pi times epsilon naught plus epsilon 1 multiplied with 1 by r square along the r cap direction, that is radial direction, everywhere. This question is from the GATE Physics paper 2021. This is a numerical answer type 2 marks question, and the topic of the question is electromagnetic theory. According to the question, consider a cross section of an electromagnet having an air gap of 5 cm as shown in the figure. It consists of a magnetic material having magnetic permeability mu equals to 20,000 times mu naught, where mu naught is the magnetic permeability of vacuum and is driven by a coil having N times I equals to 10 to the power 4 amps, where N is the number of turns and I is the current in ampere. Now it has been said, ignoring the fringe fields, the magnitude of the magnetic field B vector in Tesla rounded off to 2 decimal places in the air gap between the magnetic poles is. So basically we have to find the magnetic field vector B in this air gap. Now let us see the solution part. According to the question, we have to deal with a magnetic circuit, which is basically analogous to a electrical circuit. First, we will study briefly about the concept of magnetic circuit. We know magnetic flux lines in a material form closed loop. If magnetic flux associated with a particular distribution of currents is confined to a well-defined path, then the system is known as magnetic circuit, which is analogous to an electrical circuit. Let us see an example now. We will consider a magnetic circuit which is basically an electromagnet consists of a core material having high magnetic permeability. The number of turns in the windings is capital N. The current through the wire is I. Now we will consider a closed path ABCDA along which we will apply the Ampere's circuital law, that is dotted line in the figure. So we get a closed path integral of the magnetic field vector H is N times I. Now we will calculate the magnetic flux phi over the cross section area S in the circuit. Now according to the Ampere's circuital law, the closed path integral of H vector is Ni. Now closed path integral is taken on the closed path ABCDA. Now we know our B vector is basically mu times H vector, where mu is the magnetic permeability of the core material. Now flux is defined as B times the cross section, that is B into S. We can write our H vector as B by mu. Now B is basically phi by S, so our H vector is phi by mu S. Now we will use the equation 2 in equation 1. Now equation 2 was our magnetic field vector H is equals to phi by mu S, and equation 1 was from the Ampere's circuital law, that is closed path integral of H vector is Ni. So if we use the equation 2 in equation 1, then we will get closed path integral of the magnetic flux phi over dl by mu S equals to Ni. Now we are dealing with a magnetic circuit, so we expect that our magnetic flux phi is essentially the same over any cross section S. So we can take out the phi term outside of the integration, so we can get phi equals to Ni divided by closed path integral of dl by mu S, which is basically our closed path integral of H vector divided by closed path integral of dl by mu S. Now according to the Ohm's law for an electrical circuit, we know current passing through a circuit I equals to EMF by resistance, where EMF is electromotive force, which is defined as closed path integral of the electric field vector inside the conductor, and the resistance is closed path integral of dl by sigma S, where sigma is the conductivity of the material and S is the cross section area. Similarly, for magnetic circuit we have magnetic flux phi equals to closed path integral of H divided by closed path integral of dl by mu S. Now by analogy with our electrical circuit, the quantity closed path integral of H vector is defined as magnetomotive force, which is MMF, and this closed path integral of dl by mu S, which is analogous to a resistance term in the electrical circuit. So this closed path integral of dl by mu S is reluctance of the magnetic circuit. So we have the working formula, that is magnetic flux phi equals to mmf, which is closed path integral of H vector divided by reluctance, that is closed path integral of dl by mu s. Now we will see what happens if a small air gap is present in that magnetic circuit. To measure the magnetic field in a magnetic circuit, it is a common practice to have small air gap in that circuit. Let us consider this schematic now. In the schematic, there is an electromagnet and there is a small air gap in that magnetic circuit having length del L. Now current passing through the electromagnet is I and number of turns is capital N. Core material is iron or any magnetic material with high magnetic permeability mu. So according to our definition of reluctance, the reluctance of the core material Rc is basically Lc by mu s, where Lc is the core length, which is basically this closed path length A, B, C, D, E, F, A minus this air gap, that is del L. Mu is the magnetic permeability of the core and S is the cross section area in that core material, that is shown here. So the reluctance of this air gap in that magnetic circuit is Ra equals to del L by mu naught S, where mu naught is the magnetic permeability in this air. Here del L is very less than the core length Lc, so that spreading of magnetic flux in air gap is negligible and the effective cross section of the air gap can be taken same as that of the core material. So total reluctance of that magnetic circuit is Rm equals to Rc plus Ra, where Rc is the reluctance of the core material and Ra is the reluctance of the air gap. So it is analogous to the electric circuit where two resistors are connected in series. So in our magnetic circuit, the total reluctance of that magnetic circuit is Lc by mu s plus del L by mu naught S. Now we know the flux through the circuit phi is defined as mmf, that is magnetomotive force, divided by Rm, that is total reluctance of the magnetic circuit. So in our present configuration, the magnetic flux in that magnetic circuit, that is phi, equals to N times I, which is basically mmf, magnetomotive force, divided by the reluctance of the circuit, that is Lc by mu s plus del L by mu naught S. From here we can get the magnetic field in the air gap, that is V is equal to phi divided by the S cross section equals to Ni divided by Lc by mu plus del L by mu naught. So this is our formula for magnetic field in that air gap. Now according to the question, we have to consider this configuration of electromagnet with a air gap having length 5 cm. Now according to the magnetic circuit, the N times I is 10 to the power 4 amps. The air gap in that magnetic circuit del L is 5 cm. Now we will see what is the core length of this magnetic circuit, that is Lc. For this we will consider this red dotted closed path inside the magnetic circuit. The closed path is passing through the center of each part of magnetic circuit. Now for this closed path, we will first calculate the length of this side, the longer side. So as you can see, from here to here the length is 3 cm. So for this closed path, this length is half of that, that is 1.5 cm. And from here to here it is 3 cm. And from here to here it is the length of the air gap, that is 5 cm. And again from this to this part is 3 cm. And similarly the remaining part will be 1.5 cm. So if we sum up all of the lengths, then we will get the length of this side is 14 cm. Now we will see what is the length of this smaller side. So according to the schematic, from here to here the length is 1.5 cm. and this part will have length 3 centimeter, and similarly the remaining part will have 1.5 centimeter. So if we sum up all of this length, then we will get the length of this smaller side is 6 centimeter. So our core length will be the length of this closed path minus this air gap. So this is basically 14 times 2 plus 6 times 2, and we will subtract the air gap, that is 5 centimeter. So we will get the core length as 35 centimeter. The magnetic permeability of the core material is 2 into 10 to the power 4 times mu naught, where mu naught is the magnetic permeability of air, that is 4 pi times 10 to the power minus 7 Henry per meter. So in the previous slide, we came to know about all the quantities required to calculate the magnetic field in the air gap. So magnitude of the magnetic field in air gap is B equals to Ni by Lc by mu plus del L by mu naught. So if we put the value of each quantity, then we'll get Ni equals to 10 to the power 4, and Lc is 35 times 10 to the power minus 2 meter divided by 2 into 10 to the power 4 mu naught, plus del L is 5 into 10 to the power minus 2 meter and mu naught divided by mu naught. So if we see this expression carefully, the first term in the denominator can be neglected, as this mu is 2 into 10 to the power 4 mu naught, which is very greater than mu naught. So if we cancel out this term, we will get the simplified magnetic field, that is 10 to the power 4 divided by 5 into 10 to the power minus 2 by 4 pi into 10 to the power minus 7. So if we calculate that, we will get 4 pi divided by 5 into 10 to the power minus 1 Tesla. So our magnetic field in the air gap will be 0.25 Tesla, which is rounded off to first two decimal terms. So we have solved the problem, and we found that the magnetic field in this air gap is around 0.25 Tesla.